3 of 11.2, where we're going to incorporate some trigonometry now into our vectors. So if we were given the magnitude of vector u and the theta for that vector, we want to turn this into component form. Well, wait a minute. In order to have an angle, you have to have, if you will, two sides. So think of your xy coordinate plane. Here's my position vector. We'll just put it in quadrant 1 here. And this will be my angle theta. There's my magnitude, my distance. And my point xy is right at the tip of that arrow. So we can build a right triangle down to the x-axis, drop my perpendicular, and I can now find x and y using your SOHCAHTOA rules. So x is the adjacent side, so that's cosine of theta equals x over the magnitude of u. And here we have y is the opposite side, so sine of theta equals y over the magnitude of u. Multiply those magnitudes over to the other side, and now you have representations for x and y, and we can put that into component form. You can also take those magnitudes of u and factor that to the front of the component form if you want to shorten up your writing, especially if you got big values. And again, we can also put it in that standard basis form with your unit vector I and unit vector j for the x component and y component. So if we were given the magnitude of vector v and we were given an angle of 120 degrees, we want to put vector v in component form. So take your two representations, x equals magnitude of v times cosine theta, magnitude of v times sine theta for y. Let's plug in the values, 5 and 5. Cosine of 120, sine of 120. Now, if you recall, cosine is going to be negative in quadrant 2, where 120 is, and sine will be positive. So that would give me a 60-degree reference angle there in quadrant 2. So the cosine of a 60-degree angle is 1/2, but again, it's negative. So that'll be 5 times a negative 1/2, so negative 5/2. And sine of 120, again, sine of that 60-degree reference angle is radical 3 over 2. So multiply the 5 to the top, and there is my component form. If we were to ask to be find theta and the length of the vector in component form -3, -4, let's plot it. So again, that's the tip of your vector starting at the origin. So we're -3 to the left, down -4, there's my vector. All right, so my theta, positive x-axis, wrapping around counterclockwise till I hit the vector. And let's go ahead and find, let's see, the length, the magnitude we can do right away. So the square root of -3, or you could say 3 squared, 4 squared, because we know it's going to be positive. That's going to be 25. Square root of 25 is 5. So there's our magnitude. We'll need that to find our theta. All right, so, well, if you were going to use sine and cosine, you would need it. But you could also use tangent here, which is very convenient because you already have the values. So remember, tangent of theta, here's your reference angle, is opposite over adjacent. So that would be the y component over the x component. So -4/3 or 4/3. And then we can use your calculator, and we'll just do the inverse tangent of 4/3, which is approximately 53.13 degrees. All right. However, though, we are in quadrant 3, so we have to add, because 53.13 is here, you got to add 180 degrees to that to get it down into quadrant 3. All right, so if I add the 180, my official angle for theta is 233.13 degrees. Got to slow down here, I'm talking a little too fast. All right, a quarterback throws a football with an angle of elevation of 40 degrees and a speed of 60 feet per second. Find the horizontal and vertical components of the velocity vector. Now, in a problem like this, that magnitude is going to be your speed. So the magnitude of v is 60 feet per second. So if we think in 1 second, that will go 60 feet. We have our theta, so we can find our horizontal component, that's the x. So x is going to equal 60 times cosine of 40 degrees. Plug it into the calculator, find your answer. Vertical component will be y equals the magnitude times the sine of 40 degrees. So 60 times 40 degrees in your calculator is 38.57 feet per second. Example 9. Find the magnitude of the resultant force. That's like saying the resultant vector, and the angle it makes with the positive x-axis. All right, so whoops, doggone it, went backwards. All right, so if we want to find some of these vectors in component form, force 1, it's along the negative x-axis, so that would be negative 300 and 0. For F2, that's going to be that distance, 200 newtons right there. Okay, that's my magnitude. So 200 times my component form of cosine 60 degrees, sine of 60 degrees, which again, those are special 30, 60, 90 angles. Cosine of 60 degrees, that's going to be 1/2. Sine of 60 degrees is radical 3 over 2. So if we multiply in the 200, that'll cancel with the 2. So we'll have 100 and 100 radical 3 or square root of 3 for the y component. Now, to find the resultant force vector, right now, notice that both forces have the same initial point. So what would be smart to do here is probably could do a parallelogram, or we could take our force here, move it over to this endpoint, connect it together there, and we could do the triangle method. So there is my resultant force vector. So that would be force 1 plus force 2 gives me my F. So we're just going to add those together. So the nice thing here is since force 1 vector and force 2 vector are in component form, you add the x components, you add the y components. Negative 300 plus 100 is negative 200. 0 plus 100 square root of 3 is the same. There it is in component form. So once I have the force vector in component form, I can find its magnitude. The square root of 200 squared plus 100 radical 3 squared. Again, you don't have to put the negative in there. That's optional. So that will be 70,000 on the inside. Just let your calculator crunch everything out. Take the square root of that, and we are approximately 264.6 newtons for that force. Find the direction of F. That's the angle to the x-axis. All right, so again, taking your tangent theta, the y component, 100 over the square root of 3 over the negative 200. We reduce that to square root of 3 over negative 2. We do the inverse tangent. You get negative 40.9 degrees. But remember, your inverse tangent, when it's negative, that's going down into quadrant 4. We're going clockwise. So we're kind of taking this red vector and going in the opposite direction. So again, if you add 180 degrees, that's going to put me over to that red vector. So we are at 139.1 degrees for our theta. Example 10. A propeller plane is flying due north at an airspeed of 200 miles per hour and encounters a wind blowing 40 miles per hour from the direction of north, 60 degrees west. What is the true course of the plane and the ground speed? So 200 miles per hour, that's going to be the magnitude of my vector plane. The wind's magnitude, 40. We draw a picture. All right, so here's a long vector, 200. Short vector, this is the wind. Remember it said it's coming from a direction of north, 60 degrees to the west. So the wind is coming 40 miles an hour from this direction. So technically, we got to take this blue vector and flip it in the opposite direction because the wind is blowing in this direction. So that gives me a negative 30 degrees with relationship to my positive x-axis. Still 60 degrees there because those are vertical angles. So again, think about what's happening. Our plane is flying due north. Bam, it hits this wind. That wind is kind of a headwind and a side wind. It's going to push us off to the right here. So we can take this information down here and put it at the tip here, and we'll say, this is where I'm going to end up in 1 hour's time. So if I encounter the wind right here, and that wind stays the same for an hour, my resultant vector here in purple is where my plane's going to be at, with the same 200 mile an hour speed with trying to stay on that same straight bearing going due north. All right, so find the component form of our vectors. So our plane, 0 for the x, 200 for the y component. For the wind, looking down here or here, doesn't matter. That's going to be a magnitude of 40, and we're going to multiply that by, got to use this angle right here with the x-axis. So 40 times cosine of negative 30 degrees, 40 times the sine of negative 30 degrees. All right, so again, we can add those two vectors together. 0 plus 40 cosine of negative 30 degrees. If you don't want to put in the degree symbol, that's fine. 200 plus 40 sine of negative 30 degrees. That's my resultant vector. The true course is the direction of the resultant vector, so we need to find theta. So our theta is going to be right here. All right? Now, I know I have theta prime and theta. Now, the reason I put theta here is because of the bearing technique that they used. North, your theta to the east. So what we'll do is we're going to have to find theta prime first, subtract it from 90 to find this angle value here because these two will be complementary. So we're going to use theta prime here. So tangent of theta prime is y over x. So it's your y component over my x component. All right, so I left it as is because I want to type everything in so I get my exact values. I don't want anything rounded. Okay, so we're going to type this into the calculator. We're going to take the inverse tangent of that, and you're going to get 79.1 degrees for theta prime. Now, how I found that with your calculator, what you should do, because we're going to need to use the x component and y component again. Here was my calculator entry. I plugged in the x component right here, and I stored it for x. The store button is right above the on button. So you type in the expression, the store button, x, and enter. Then for the y component in the numerator, you type in the expression, the store button, alpha y. And if memory serves me right, y is above number 1. So that's 180. So having those two stored, now when I want to find my inverse tangent, I'll just type in y over x, and there's my angle. So again, subtracting 79.1 from 90 gives me 10.9. So here's the bearing that we're looking for. That's my true course. My true course is north, 10.9 degrees to the east. My ground speed is going to be the magnitude of that resultant vector. So now remember, that's the x component squared plus the y component squared. We have that stored in our calculator. So for our calculator, you just have to type in the square root of x squared plus y squared. You don't have to enter this all again because we stored it. And that gives us 183.3 miles per hour. And that's the end of section 11.2.